Are we good?
Yeah.
All right. Hi, everybody. I'm David. I don't know some of you, so you probably don't know me. I'm a postdoc here. And so the topic for tonight is a very quickly put together, unprepared, so I'll probably get it wrong, so please be vigilant, overview of how to do normalization by evaluation, which is a fancy way of saying we're going to start with an interpreter for untyped lambda calculus and build it up to a machine that can decide whether two typed lambda calculus terms are equivalent with, in a way that I'll talk about in a little bit. And the reason why you'd want normalization by evaluation is that it's a technique that you put inside of like a proof instant, for example, when you need to check whether two types are equal to each other. That can involve computation. And so if you want to include what are called eta rules, which is sort of a type-directed notion of equality, then normalization by evaluation is probably the easiest and most direct way to implement it that I know about. It also has uses in theory side, which isn't really what I use it for, but I can point you at places to read about it. So the agenda for today is over there. I'm going to start off talking about what is normalization, briefly, and then after that, we're going to show how to derive a normalizer from an interpreter, and the interpreter is already on the whiteboard. And once we've got that, then we'll add this notion of sort of typed equality in addition to untyped equality. So first off, let's say we have some notion of syntax. In this case, lambda calculus. We have expressions are variables, or they are anonymous functions, or they are function applications. And we want to talk about which of them are equal to each other. We have one rule which tells us when they are equal, and that rule is what we call beta. In other words, that an application of lambda x, some expression, to some other expression is equal, which is to say it's exactly the same thing as the result of substituting E2 for x in E1. And then we sort of course, pipe this around to all of the different occurrences where an E can be, so we can do it in each position of an application, and in the body of a lambda, wherever we want, right? This is just a theory which lets us do equality. So you can do all the normal equality things, and I'm not writing them all down because they're boring. So what might we want to do? What we might want to do with this is check whether two expressions are equal. And the one way you can do that is find every occurrence of a thing that looks like this and do this. So in other words, you can read this equality as kind of going from left to right, even though it's equality, which means you can flip it around, it's symmetric. And then once we get down and we find everything and we get to the spot where there's no more of these reducible expressions, read x's left, then we've got a program that we're done with. And then if two programs are exactly the same under some renaming of the bound variables, which is say alpha equivalent, then we know that they were the same program in some sense. And unfortunately, we don't really have an algorithm here yet, right? We want like a fast way to run this kind of thing. So let's start off with the kinds of interpreters that many of you have seen before. So we define a notion of value, and here this box is a closure, so it's the name, and it's so the result of evaluating a lambda. So we've got the name for the variable that we used, we've got the expression in the body, and then we've got the runtime environment which gives the values of all the free variables. And then we can write an interpreter which constructs these values. So this double bracket sub row thing, which I'm going to call eval for historical reasons. If we want to eval of x, then we look up x in our runtime environment. So you can think of it as a mapping from the variables that we've got available to their values. If we have a lambda, then we construct a closure. So we package up the useful information along with the runtime environment in this box. And if we want to do an application, then we call apply on the result of evaluating the operator and evaluating the operand. And apply is our helper here. And apply of a closure to some value is the result of calling eval on the expression inside the closure with the environment from the closure extended with a mapping from the variable on the lambda to v, the value of the operand. Any questions? Please feel free to ask questions at any time. Okay.
You're intentionally or unintentionally mixing call variable by name?
here. I don't care. We are beyond that level of abstraction here. So this is great, right? We can throw in an expression and out pops a value. But a value is not really a normal form because normal forms are expressions themselves. And clearly this weird box thing is not part of the syntax of our language. It's a V, not an E. So if we want to then turn this thing, if we want to then turn one of those values back into an expression, how do we do it? Any suggestions? So I have a suggestion. What color are we using? I'm using red for this. The agenda has colors for the various steps. So what I'm going to do is I'm going to call the process of converting a value back into syntax that represents it, reading back the syntax from the value. And we use an R for that. So we define this operator called R, and R of one of these closures what we do is we generate some fresh name, and I think the convention in Indiana is to put a hat over those. So I'm going to just indicate them that way. So we say lambda x hat. And now, what do we put into, how do we know what the body of that lambda is? We use apply, right? So then we say that, then we're going to call R on the result of apply of our value here. And what are we applying it to? We can't, right? Because we need to give it a value. So we're missing something important. And what we're missing is what's called a neutral term, or a neutral expression. So I'm just following to make sure I do all this right. So a neutral expression represents one of these computations where it kind of got stuck, right? So if we're in the body of a lambda, and we have an application of some variable f to some other variable x, we don't actually know what closure f is going to be yet. So we need a way of representing that this is a variable that stands for some concrete function, which we can then eventually evaluate. So now I'm going to add another type of thing, which I'm going to have some two-letter meta variables here, and I hope you can accept it. So NE is going to consist of variables, but not only variables are neutral, right? Because variables can be applied to stuff. So we also have that NE can be an application of an NE to what? To a value. And so these two are going back and forth. And the reason we're saying that this is a value is something that we'll get to later. So now that we have this notion of neutral expressions, now we have something that can be put in here. And so we can say that we're going to stick in x hat. But apply also needs extension, because apply right now only knows how to deal with closures. And we've just extended the grammar with a notion of neutral things. So what should apply do when it hits a neutral thing? I'll say some neutral thing and some value v. The solution is that we make a bigger neutral thing. We make a neutral application. So then we say that this is going to be NE of v. So we've just sort of accumulate these arguments as we go until we find out what the function actually is, and then it becomes a closure, and then we could evaluate it further if we wanted. Yeah?
So why did we need this second line, like right now? I can't see why we need NE.
So we need the NE because this x here is a neutral expression. So it's part of this NE grammar right there. And so that means in the body of that function, we might apply the argument. So for example, say we had lambda x, xx. When we want to read that back from its closure, yeah, let's actually step through it. Thank you. So we get lambda x. We want to evaluate lambda x, x of x, in some empty runtime environment. And what we're going to get back is this is going to be a closure of x dot x x in that empty environment. And now we want to read that back. So we pass that into readback. So we stick an R around everything. And now we are going to have that becomes lambda of some fresh variable x hat of app of our closure.
R of app, right?
Or, sorry? Yes.
Still missing an app.
Yeah, what happened to the
I sure am. Okay. Of x hat. And now the next step after that is that we're going to be doing R of x with x goes to x hat, right? Okay. And the next step after this is
Oh, and now that's where we need the yeah.
exactly. So we have R, and now we're going to see how we evaluate an application. The way we evaluate an application is we call apply. So now we have R app of the result of evaluating x, where x goes to x hat. Apply to x, where x goes to x hat. And what this emits is the neutral x applied to the neutral x. So now, right, so this is going to become x hat. Right, so we have app of x hat, and now we've reached something that isn't a closure, it's a neutral, namely x hat, the variable. And so then we need to know to build up this sort of this syntax of an application to be performed. So that becomes x hat of x hat. And now we're in a position where we can read it back. Or are we?
Where did lambda x hat go?
Right? So what this means, this clearly demonstrates that we need one more thing in readback, which is what do we do in case we get NE? And I'm going to call a helper, which I'm going to call R sub NE of NE. I'll just call it R sub N. That'll be good. So, how do we read back a neutral expression? The way we read back a neutral expression is to say R sub N of some x is precisely that x, and R sub N of a neutral application is the R sub N of the operator applied to R of the value. And if we go, so now we know how to read this back, and it's going to read back to x of x, x hat of x hat, and so we end up with lambda x hat of x hat. The point gets crunchier when you have types on it.
Right.
Yeah.
Here's a question.
Oh, I'd say I'm following along with what we're doing at a small step level.
Sure.
Could you back off and give me an intuition behind either why I'm calling these neutral terms or at a larger level what it is that I'm getting by having readback? I feel like you
Sure.
say
Sure.
that out loud.
Right. So one of the ways by which we could implement testing for this equality is to repeatedly scan an expression and find every redex and perform sort of one step of data. And like back out, rebuild everything, scan it again. Back out, rebuild everything, scan it again. To do that, we need to implement capture avoiding substitution, which is tricky, and it's also slow. So instead, we can use an interpreter, like the normal ones we do, where you just use an environment to find values, and compute a value. Having computed a value, though, we haven't found a normal form of an expression, right? Like we've gotten part of the way there, but we need to do more. So then, in order to transform the value back into syntax, we use this reading back procedure. So then the composition of evaluation and reading back gives you normalization. So another way to think of it is that these values are a representation of only the normal forms of our expressions. Where the normal form is when you take some equational theory over your syntax and use that to sort of divide it up into buckets. And then for each bucket, you pick a canonical representative that you know how to find for any expression that's in that bucket. And then that canonical representative is what we call normal form. Then to check if two things are equal, you find their normal forms and see if they're the same. And this is the thing that you do need to do some of the time. Does that help? Sure. Okay. So now we can say that I'm going to erase this example and write this thing a little bit. So now we can say that to normalize a thing, so norm of E equals R of eval of E in the empty runtime environment. That needs parentheses. So we started with an interpreter, we now have a normalizer. The next step is to add a more interesting notion of equality. Because this equality right here doesn't have a lot of the things we might actually want our equality to do for us. For example, if we know that something is a function, then we might want like an eta rule to make it be equal to eta equivalent functions. And this was blue. So to get started, we're going to add. So I'm going to underline an n here. So the n is sort of a meta variable standing for any natural number, and the underline means make that number into an expression. So it's sort of the injection from the natural numbers to our syntax, just because if we have enough time, which I don't think we will, but maybe we will, I'll want to do some arithmetic, and then this underline is really nice to have. So we're going to add natural numbers just because it's convenient to have some base type when you're going to do type lambda calculus. Now, our beta rule has got some typing constraints on it. So we're going to say that two expressions are equated by some particular type. And so the type version of beta here, we're first going to need to know that in gamma extended by x, a, I'll probably give you a grammar of types as well. So we'll have, I'll call them A and B, and they're going to be nat or A arrow B. So if we know that x is an A, and we can conclude then that E1 is in B, and we know that E2 is an A, then both of these expressions here have type B, and likewise they are equal to type B. I'm seeing a grimace. What's up? Are we okay?
This is just the part of homotopy type theory that blows my mind. I just remember this, like the equalities of type B.
Yeah. So the idea here is that types aren't just collections of things. They also tell us which of those things are equal to the other ones. And this is a very sort of Martin Löw type theory view of the world, but that's what I like to use these things for, so that's how I see the world. But what the nice thing about having a typed notion of equality is that it then allows us to add rules that are driven by the type as well. So we can add another rule here where we can say, given that f is in A arrow B, then we know that A arrow B equates f with lambda x fx. And that's sort of our eta expansion. And then so when we're inside of our, the nice thing about building this into our notion of equality is that when we're inside of our proof assistant, it'll figure this out for us so we don't have to go prove it. And this doesn't work for every kind of type theory or every proof assistant. It's like you don't get to use this in Coq, for example, but you do get to use it in Agda and in Idris these days. And generally these are very convenient to have, and you want to have a meta theory that supports them as long as you're not paying some other price, which you may or may not. So how are we going to, okay, so this is beta and this is eta. So if we're going to implement this, given that we now want our normal forms to talk about both kinds of equality here, that means that the normal form for any function has a lambda at the top of it. Right, so, and that's because we're sort of determining that the normal form at the arrow type is always fully eta expanded. So this is what people call an eta long normal form. And both the blessing and the curse of normalization by evaluation is that it spits out eta long normal forms. So it's a blessing in that you get eta equality, and there's corresponding eta rules for lots of other types. It's a curse in that it can make very big syntax trees, which take a long time and slow things down. And it is also a curse because you can't use it with a theory that doesn't admit eta.
What part about this is slow? Exactly?
You might, so when you're doing, like, let's say we have f, which is in nat, arrow, nat, arrow, nat, arrow, nat. And gamma's got just f in it, which is like the appropriate, which is just this type as well. So this is not in normal form, because it's not eta long. If you want to make this thing eta long, well, first off, we got an arrow here, so we expand to lambda x fx. But now this x here, this occurrence of x, that's got a function type, so that needs to be expanded. So we end up with lambda x dot f of lambda y dot xy. And now do we have any neutral terms anymore that have a function type?
Okay. I guess maybe
Yeah.
my related question would be if this can lead to performance problems, why was a choice made to go eta long instead of, I guess, eta short?
Yeah. So it's eta expansion plays a lot more nicely with a lot of types than eta reduction does.
Okay.
So like the corresponding rule, if you have a product type, for example, would be that like if you have some pair P, then it's equal to the pair first P, second P. And like to eta contract this, then you'd have to go do like an equality test on those and see if they're the same, and then you could do it. And,
Okay.
And even worse.
So there's trade-offs involved.
Yeah, like say you have some arbitrary inhabitant of the unit type, the corresponding eta rule there is just that it's equal to the sort of default constructor. How do you eta contract that? Who knows? Whereas eta expansion just plays very nicely. And the reason I want the eta equalities is because then more things are equal in the way we don't have to prove, instead of the way that we do have to prove. So we remove work from humans and place it on the shoulders of the machine, which is generally a good idea. Okay. So now that we've got our extended notion of equality, then not all, these things our evaluator needs to be extended, our notion of value is going to need to be extended, and so on and so forth, and reading that. So we have one more value, which is just that any natural number literal is a value. We're not adding any neutral forms because you only add neutral forms when you add new elimination rules to your language, and we haven't added any way to eliminate the natural numbers, which is to say like recursion over the math or something like that. This is just all we have. We can put 5 there, but we can't add it to 7 yet. So when we interpret now, our nats just go to the corresponding nat, as we would expect. Apply doesn't need anything fancy because that's staying the same. But now, where do we put our eta expansions? We need like a hook to hang them on. And in order to make eta expansion happen, then we need to know where we have a thing with a function type. And that information is not preserved through the process of evaluation right now. So what we do here is we introduce 2 operators, and this is sort of the standard notation for them, which I don't very much like because it always confuses me. And I'll probably get confused today, but I figured since I'm giving you an intro in the hopes that you'll be able to read papers about this stuff and figure them out, I'm going to try to use the standard things to the extent that I can. And I always get which one is which confused, so I've got a little note here to myself. Right. So this right here is called reflection, and it takes neutrals to values. Right? So values no longer barely contain neutrals, but instead they contain this form here, where we say what type they have. And we have another way of writing things, which we call a reification. And the reifications are used to tag values with their types. So, in other words, every time we've got one of these here, we're now going to replace that with a no for normal, or for a representation of a normal. And we can say that normals are equal to the down arrow at some type A of a value. And this means that when we read back this application, we can perform eta expansion as we hit the type annotation. You can think of this as like a way of plumbing the types through all the places they need to be for it to work. Another way you can think about it is that when you have a neutral expression, which is a variable, we're pulling that out of gamma at some point in time. So we know what type it has. And then when we build up further neutral expressions, we can then compute their types based on how they work. So you can see this as a way of relating free and bound variables according to their types, if you stare at it hard. So now we need to extend these things to work the right way. So app doesn't just get a neutral directly. Instead, app is going to get an up arrow in front of the neutral saying what type it has. And if we're doing application, if our program type checked correctly, then we know that the thing here is going to be a function, so we get to write a arrow b of some ne. And now that we have this neutral application here, on the right-hand side, we need to construct the appropriate thing, right? And so how do we do that? Okay, so what we need to do here, so what we're spitting out of apply is we're going to spit out a value, right? And this value is still going to be neutral, right? We need to spit out a neutral application. But what type does a thing of type A or B apply to some other thing which we know is going to be of type A? Yeah, it's a B, right? So we're still neutral. So that means we've got our up arrow operator, and it's going to be of type B. And inside of that, we now have our neutral application. So that is our NE. And it's being applied to, it has to be applied to one of these no's, or one of these normal things. And a normal thing is a type annotated value. And what type does its argument have in this case? A. A, exactly. We apply this, I'm going to write a lot of parentheses because I like parentheses. And I'll have an A here applied to that B. Right, so what we've done is we've pushed the types in through the application and kept track of what they are. And that's going to allow us to do, yeah.
Would this work differently if you didn't attach types to the up and down arrows? It's useful here, but only for the purposes of plumbing types through other arrows. So I'm wondering if there's a situation where it would fall apart if you didn't have that readily available.
If we didn't have our types available, then we wouldn't be able to have full eat-along the forms, because that relies on knowing what the types are.
Sure, but you're also carrying gammas around, right?
Yes.
And those have types in them.
Yes. So you
why can't you just get it from gamma?
So you could invoke your type checker recursively from your evaluator to recover that lost information. I think that's likely to not work out to be very performant, especially if you're doing like recursion.
I'm just curious of the choice of the things you did annotate with types, because you have arrows of type that, for example,
so this
binding for a lambda that didn't have a type. So
sure.
It's a bit interesting to see what choices you made.
It's a little bit fascinating. The idea is to not have overwhelming notation. And in a real system, you're going to have to make choices and figure things out. All right? Okay. So now we've got what it means to apply a neutral thing, and we've plumbed all of our information through. And now, R, we're going to change R so that it's reading back normals rather than values. In other words, these things, they're all going to have a down arrow saying what type they have. So, in this case, we've got a down arrow saying that it's an A arrow B. In this case, we've got a down arrow followed by an A arrow B, followed by an up arrow at type mat. And then in the third case that we're going to have, that's a down arrow mat and an up arrow mat. And the third case that we're going to have is going to be down arrow of some mat and our good old friend natural number literal. So then in this case, we need to know how do we plumb the types through in the readback case, right? So now, what we're doing sort of fundamentally is we're first kind of case splitting on what type we're working at. And once we know what type we're at, then we can make a decision as to how to read it back. So a sort of fundamental insight that we get is that eval is kind of what gives us beta, because that's how function reductions happen. And readback is what's getting us eta expansion. Because that means each type gets to say what its normal forms are as syntax, which is what we want if we're doing a type-driven notion of equality. So in this case, if we have a neutral natural number, then we just go back to our neutral readback the same way we would. So the types have kind of started out on the variables and on the outside, and when they meet in the middle, they annihilate each other. Yeah.
So would you need more cases in the middle if you had another base type besides naturals?
So what you would typically do is each one of these types, you would have a case for what you do for its actual value. So I would always write this one first. Mm-hmm. And then at the end, you can have a catch-all case for all the remaining neutral terms. And if you want to debug your system, then you also do a type equality check when you hit that case.
Okay, I guess I was a bit confused because that middle cases are n instead of like R of A8 or something.
Yeah, so I could have written something like R of... Okay. We would never catch it in this case because this is going to be matching anything at all once we update it a little bit. Okay, yeah, that'll happen.
I'll be patient.
Okay. So then this is going to be just n. And now we've got the interesting case, which is what do we do in the case of a value? Well, in the case of this, we actually don't need to check sort of the form of the closure we got. We can just put v here, and then we can sort of V here. Okay. And then app is going to be taking normals, so we need to know the type, so we pass that in. And then, of course up here we would need, sorry, app is taking values. This is all. Okay. So now we rather than looking and seeing did we get a closure and then doing the right thing, instead we say we know we had a function. That means it's the kind of thing we can apply, whether it's value or neutral. I mean, app apply already knows how to deal with both neutral and with closures, so we can just pass it in, and that is what triggers eta expansion. So types that have eta rules will typically have a readback case where you look at the type and then you have just some arbitrary value, and then you do a constructor around an elimination form, where the elimination form is the version that knows how to deal with the neutrals, like apply here. And you could have similar things for first and second projections from a pair, or for recursion on natural numbers, or whatever it is. The way it looks is that you write it the normal way you would, and then add a case for how to deal with neutrals, which is that it builds up a version of its own syntax. So now, we have a little bit more work to do here, because normal forms are with respect to some type and in some context. So what we need to do is say that, we'll say that norm, which I left a little more space, is going to take some gamma and some a. That's gamma a, and then the expression that we're normalizing at type A in context gamma. And then the way that we determine that normal form is that we say R of, we annotate this with an A, because we know we need to know what the type is. Then we still call our evaluator of E. And then what happens if E contains a reference to a variable in gamma? What happens is that we need to kick off this chain of building up these big accumulations of neutrals. And so the way we do that is I'll just call this thing, let's call it N of gamma. And then we define N sort of just recursively over gamma. So N of the empty gamma is the empty row. And N of gamma extended by x colon A is going to be equal to N of gamma extended by, in the fact that the x points at the neutral type A x. So we seed the initial runtime environment with the appropriate notion of free variable, which is a neutral thing with the type annotation, and then kick off the machine, right? Because what variable is bound or what variable is free kind of depends on your perspective. You know, if you're sort of crawl halfway down into a program and look outward, then you see gamma, and if you look inward, then you see, and those are the free variables. And if you look sort of inward into the program, then you'll see like lambda x, lambda y, lambda z. And you'll know that those are the bound variables that eventually would pull into gamma if you crawled in past one of them. So the idea here is that we're always doing our normal forms with respect to a particular spot where we're standing, because we have some free variables floating around, and we want to know how things, which things are equal to which other things with respect to those already known free variables. And so we have to sort of start off with those being something that we know how to look up in our evaluator. Any more questions? Okay, so the next step, let's just walk through how we'd add one more elimination form, because I think that's what makes it quick. We're going to add one more expression, which is going to be called rec sub A E. So what this is it's the ordinary recursor over the natural numbers. So this is going to be some nat this is going to be some base case, what you do when the nat is 0. And this is going to be some step. So when the nat is n+1, then you apply the step to n and to the result of recursion on n with otherwise the same arguments, and then get back an answer. And then we put the a here because we're going to need it. So our notion of values here doesn't change at all, right? Because we already had the appropriate values associated with the nat type. And our notion of neutral terms does change, because every time we add an elimination form, we need to add a new kind of neutral expression to deal with it. So I'm going to call those rec sub a, and then the thing that we're eliminating, like the target of the elimination, the spot where that goes, we put a neutral, and everything else we put in all. And that is neutral recursors. We need a notion of equality for recursors. So we're going to say if we know that B is in A, and we know that S is in nat arrow A arrow A, then we know that rec sub A of 0 BS is equal to B at type A, and then dot dot dot, because you just copy paste these down to this line right here. We could say gamma of rec sub A of some n+1 of B and S is equal to S of n and rec sub A n B S. Okay. So we might want to like call that like iota 1 and iota, I guess is the way you say. So this is sort of the ordinary way that you do recursion over natural numbers. So now we've got enough to do some pretty interesting things. Like we can write acronyms now in our language, which is kind of nice. So as far as the interpretation goes, we have one additional case because we have one additional kind of syntax. So we want to say rec sub A of, what do I call it? Let's call it TBS for target, base case, and step in row is going to be equal to, and then we follow our pattern that we define a helper to take care of actually implementing the elimination. So we'll call that helper R sub A of eval T row, eval B row, eval S row. And now we need to define R sub A. So we know what R sub A does for actual sort of canonical nats, like concrete numbers. So if we have R sub A of 0 B S, that'll just be B. R sub A of n+1 B S equals app, right? Because those things might be neutral themselves, and so we're over in sort of semantics land, so we need to run our function appropriately. And then we do app of S to app of sorry. It associates the other way. So app of S to N to R sub A of N B S. And then we have our final case, which is for a neutral natural number. So a variable standing for a natural number or like an application of some variables to some other stuff that will eventually be a nat once we get their values. So then we're going to have recursion of upnat of NE B S is going to be our neutral version here, right? So we have our neutral over there. That becomes up A. And this is where we needed that A, right? Because we don't have it anywhere else here. And that's going to be up A of rec of any down A of B, and then down nat arrow A of S. And then readback of neutral is going to do the exact same thing that we think. So we're going to say R read neutral of rec A of any down A B down actually E S is going to be equal then to rec sub A, right? Because this sort of space here is the elimination form application. So we do rec sub A of R sub N of NE, and then normal readback, because these are normals, right? They're annotated with their type. We can do R of B, R of S. And we're done. So then if we're going to then throw in some function that does addition or something, this will normalize it for us and figure it out. And now it's 5 o'clock, and so you're all entitled to leave. And thanks for coming.
Let's thank our speaker. All right, eat or bug the speaker.
Yeah. Yeah.
Don't erase it.
Sorry?
Don't erase it.
I'm not going to erase it right now.
You still have a whole board there.
Yeah.